The constituent particles in a crystal may be thought of as solid spheres, and in this video we shall try to understand the close packing of spheres in a 3D space, leaving minimum vacant space. Packing in one dimension. There is only one possible linear one-dimensional arrangement possible with spheres. They queue up linearly, each sphere touching the adjacent spheres like this. Packing in two dimension. To arrange spheres in two dimension, we take the linear one-dimension arrangement that was shown previously. There are two ways by which we may arrange the spheres in a two-dimensional platform. They may be arranged like this. Note that each linear arrangement are aligned vertically. Here the vacant space is this. Now in this packing, the spheres take up only 52.48% of the available space. Here a single sphere touches four other spheres. If we join the centers of the spheres, we get a square. Therefore this packing is called square close packing. A second way of arranging the linear one-dimensional arrangements is to keep the spheres of the second linear one-dimensional arrangement in the depressions of the first, like this. Here every alternate linear arrangement has the same alignment. These are the vacant spaces, which is visibly less than the square close packing and hence more efficiently packed. In this packing, the spheres occupy 60.4% of the available space. The voids created in this packing touches three spheres forming an equilateral triangle and are called triangular voids. A single sphere touches six other spheres, and by joining the centers of these spheres, we get a hexagon. Therefore, this packing is called hexagonal close pack. Packing in three dimension. Taking square close pack two-dimensional layers. This is done by placing a two-dimensional layer just above the first layer and so on. All the layers are vertically aligned. Taking hexagonal close packing two-dimensional layer. The first layer contained red colored spheres indicating the alignment of the layer. This alignment is called A. These are the void spaces of the layer. We have to place a layer on top of this layer. For efficient packing, we will have to place the second layer in such a way that the spheres are exactly over the triangular voids of the first layer. Only these triangular voids can be covered. The spheres of the second layer are blue in color, which indicate that this layer has different alignment, and this alignment is called B. We can no longer see all the void spaces created between the two layers. In order to overcome this problem, we will make the second layer transparent. Now we can clearly see the two different types of voids created by these two layers. These are called Tetrahedral Voids, marked by the letter T. And these are called Octahedral Voids, marked by the letter O. The Tetrahedral Voids are created by four spheres. First, we make the spheres a little smaller in order to understand the shape. Then we join the center of the spheres by straight lines. The shape is a regular tetrahedron. So the void is called tetrahedral void. The octahedral voids are created by six spheres. Here also we make the spheres a little smaller, then join the center of the spheres to get the shape. The shape is a regular octahedron. Placing the third layer. This can be done in two ways. These are the triangular voids of the second layer that are not involved in making octahedral voids with the first layer. By placing the third layer above these voids is one way of placing the third layer. If we do this, we can see that the first and the third layer have the same alignment A. With similar reasoning, we keep a fourth layer on top of the third layer and see that the second and fourth layer have the same alignment B. This pattern of close packing is called ABAB type pattern. We make spheres a little smaller and join the centers with straight lines to understand the shape. It is my belief that this is the unit cell of this close packing because it is the smallest unit that may be repeated to form the entire crystal. The top of this unit cell has the shape of a rhombus having gamma equal to 120 degrees. Three such rhombus form a hexagon. For a better visual cognizance, this shape is taken as the unit cell of this close packing, which is called hexagonal close pack or simply HCP structure. Another way of placing the third layer is to cover the octahedral voids of the second layer by placing the spheres of the third layer above the octahedral voids made by the first two layers. The alignment of the third layer is different from the first two layers, and so the color of the spheres have a different color, that is green color. Let this alignment be called C. Using the same reasoning, we can cover the octahedral voids created by the second and third layers by a fourth layer. It will be found that the fourth layer has the same alignment as the first layer. So this pattern is called ABCA type pattern. Now again, making the spheres a little smaller and joining their centers by straight lines, we get the shape of this packing like this. The unit cell of such a packing is this. This is nothing but a face-centered cubic lattice. So this type of packing is called cubic close pack or simply CCP or even FCC structure.